This video gives an introduction to the paper Lightweight Video Denoising Using Aggregated Shifted Window Attention. This work was conducted as a collaboration of the Technical University Graz and the University of Bonn. State-of-the-art attention-based denoising methods typically yield good results, but require vast amounts of graphics memory and usually suffer from very long computation times. Especially in the field of restoring digitized high-resolution historic films, these techniques are not really applicable in practice. To overcome these issues, we introduce a lightweight video denoising network that combines efficient approximate 3D convolutions with a novel attention mechanism, termed aggregated shifted window attention, which is based on the memory-efficient aggregation of self and cross-attention across video frames. Our general network architecture is inspired by ASwin convunet. Like SCUNet, our denoising strategy combines the local modeling ability of residual convolutions with the non-local modeling ability of efficient shifted window attention. As the main building block of the network, we incorporate our proposed ASwin ACS-conv block. The proposed aggregated shifted window attention extends recent attention mechanisms to effectively process video data. We compute self-attention within a frame and cross-attention to adjacent video frames and aggregate the information using a residual aggregation scheme. The compared windows are equal in the case of frame-wise self-attention, whereas, for cross-attention between frames the window is shifted along the frame dimension, or in other words, only a temporal offset is applied. The fusion function H consists of a linear layer used for feature reduction of the channel-wise concatenation of the input, followed by layer norm and a subsequent multilayer perceptron. We highlight that the same fusion function is used to aggregate the attention for all considered temporal frame shifts. The final attention is obtained by function G, consisting of the channel-wise concatenation of the initial feature and the frame aggregated attention, followed by layer norm and another MLP. Consequently, our proposed attention mechanism leads to a constant memory consumption during inference, independent of the number of processed frames. Although not specifically designed for additive Gaussian denoising, we conducted preliminary experiments using Gaussian noise on Davis 2017 and SET8 to evaluate the performance and runtime of our method compared to other state-of-the-art, non-blind, Gaussian denoising methods. We could show that our model provides by far the best trade-off between performance and runtime and is therefore very well applicable for the task of high-resolution cinematic video denoising. The proposed method is designed for deep blind real-world video denoising, where we particularly focus on noise in digitized analog historic films. Since no ground truth exists for real digitized videos, the generation of synthetic realistic data of clean noisy video pairs, properly representing the distribution of real noise, which includes the noise specific for digitized analog movies, was necessary. For evaluation, we used 10 high-resolution sequences of digitized analog film footage, exhibiting different unknown noise types of varying strength. To get quantitative proof of the superiority of our approach compared to other state-of-the-art methods, we performed a no-reference image quality assessment on the denoised real videos. Moreover, we conducted a user study to further evaluate the visual denoising quality as well as the temporal consistency of the resulting videos. We compare our approach to several state-of-the-art real-world video denoising techniques including both academic and commercially available methods. We use the state-of-the-art, no-reference image quality assessment metric, MUSIC, which is computed by a transformer-based deep learning model. It can be seen that our method performs best among all compared real-world denoising techniques. The conducted user study, where participants were asked to choose the best video sequence in terms of denoising quality as well as temporal consistency, showed that our model also visually outperforms the other competing methods. Here you can see qualitative denoising results of 2 real digitized videos obtained by our approach compared to the original noisy video.